I wanted to know who has heard about Sun Studio, but now all must raise your hands. You should all raise your hands because you have heard today about it. And who has used it? Okay, a few people. That's nice. One in the first row. So here's the outline of my talk. I will very short introduce DTU for those of you who haven't heard where DTU is and what we are doing. We are a technical university educating engineers. We were founded in 1829 by Hans Christian Ørsted, and we have undergone a major change in our structure last year because we were merged with 5 research institutions all over Denmark. And this is shown on the map here. Before we were at the red spot, and now we are everywhere in Denmark. People at DTU, they do a lot of research, for example, in windmills, fluid dynamics. They also tried to put this big beast here on the diet because it was too heavy. We have a group doing some optimal topology optimization, how much material you can cut away to make this thing a little bit lighter and still make it fly. And those are the heavy users in our system. But to come back to the topic of my talk, and I think Ken Edgecombe yesterday made a good remark that we need to educate people in scientific programming to make better use of our hardware. And the first part of my talk will cover how we use Sun Studio in education. At DTU, we have started a course some 4 or 5 years ago. First it was called scientific computing, now we call it high performance computing. And it's all about tuning your application and also how to make use of multi-core and SMP machines. So it's sequential performance and OpenMP. Those are the 2 big topics in this course, and the students should learn to write efficient code, sequential code, but also to put it into parallel versions. And we have also the necessary hardware mix at DTU, so the students can get some hands-on experience on different machines. And Sun Studio for me is a very important tool when I'm teaching those topics. Here's some excerpt from the curriculum of our course. So. First, we introduced the students to how does a cache-based system look like and what is important about data and caches and all that. Then we introduced them to tuning techniques like all those loop-based techniques, unrolling and so on. Why does the process of pipelining, how does it work? What in your code can prevent to pipelining, and so on. And we need to do this to get the students get a feeling for how a modern computer works. And they don't get this in the other programming or computer science courses. They learn all the things about Java and threads, but the gory details, how a CPU and memory and everything is glued together, they don't get in those courses. And we try to give them a course here where we talk about those things. But what we typically also do is we tell them they shouldn't do those loop unrolling yourself because the compiler will do it. And that's very not very satisfactory for the students to learn the technique, and then we tell them the compiler does it. And you can't even see it because you compile your C code into an object file or an executable, and that's it. And then you cross your fingers and hope that the program runs faster. So the compilers usually are a black box, and the students don't like it. Especially engineering students, they want to know how it works. I think if you give one of the boxes you have in the back to an engineering student, they will always open the box as the first thing. They won't push the button and start it, they will open it and look into it. And I think that's the way engineers think. Sun Studio is very different with that respect. Sun Studio has a very nice feature that's called compiler commentary. So the compiler tells you what it has done trying to optimize your code, or why it couldn't optimize. It does this by annotating your source in the object file, and there's the tool to make those annotations visible on the screen. And on the next few pages I have some example. I guess it's very hard to read from the back, but this is a 5-line C code that is written Fortran style, and it has some issues. The loops are in the wrong order, and I could also improve or give the compiler some hints that those pointers don't overlap. then I could get better performance. But this is one of those what my professor calls Mickey Mouse examples, something where you can learn something. So you compile this code, and then you use this tool that's called source to look at those annotations. And I marked the annotations here in a different color. It's blue. Does this thing work? Yeah. So it tags all your loops. All your loops get a specific, a special tag. So the first loop is L1, the second loop is L2. Then it says it has unrolled this loop 2 times. And it has 2 loads and 1 stores the number of prefetches. It does 1 floating point addition. That's right. And it also gives you a number here what is called steady-state cycle count. And this number you want to make this, want to minimize this number to get the best performance. So as I said, this code has a problem. The loops are in the wrong order, but the compiler hasn't reordered those loops. And the reason for that is that I didn't tell the compiler that those pointers up here, they don't overlap. So the compiler is very conservative. It has to be. I could change my code, but I'm lazy. There's a nice compiler option. It's called restrict. So instead of putting the restrict keyword in here, I tell the compiler all my pointers don't overlap in this code. And now the compiler does the right thing. It says L1 interchanged with L2. Perfect. My cycle count went down from 5 to 2. So I should expect faster execution of my code, and it even unrolled the loop deeper from instead of 2 times, 4 times. And that's really nice because a very simple change, changing a compiler option, I can see the result in the source code annotations. I cannot do this without compilers. I also can control the unroll depth if I want to, and I can see it in the code annotations, and I can probably also see it in the performance when I run the code. And what I said before, if I have a problem that the compiler cannot schedule my loop because there's an inhibitor, the compiler commentary will also reflect that, because here it says function not inline because the compiler has not seen the routine, but the consequence is that the loop cannot be pipelined because it contains a function call. So very useful for teaching. So compilers are no longer a black box, and you can see what the compiler tries to do, or what it has done, what it can't do. And then you can take action as a programmer, like for example, switch inlining on to get this loop pipelined again. Code changes, choose another set of compiler options. More reasons. With this way of doing this, the annotations stay always with your object file, so you can review them at any time. I know that other compilers, like the Intel compiler, that has some words flags, and then you get all those messages at compile time. But if you don't save them into a log file, they are lost. And you have to have 2 windows open, one with a log file and one with a source, and you have to match those line numbers. That's not very convenient. And I'll show you in a minute the performance analyzer. In the profile, you can see the profiling of your code and those messages in the same window. There are some other tricks. Skip that slide because I don't have much time. The performance tools. With Sun Studio, you get also a bunch of tools that's for analyzing your performance. There's the analyzer, that's the GUI front end, but there are also some command line interfaces, collect and print. And this gives you profiles on the source line level. Some timeline analysis, and I'll show you some pictures. And I find those tools very intuitive and easy to learn, and my students can also say that those tools are much more intuitive than other tools available. And you get hardware counters and other things as well. So here's a profile in the analyzer window. So you get the typical profile, your function names or subroutine names, and then you get the CPU time and the wall clock time. And if you click on the function name, and you can go to the source, then you can highlight your hotspots in the source on the source line level. And another feature I like very much is the timeline. So you get a stack trace of your code execution at any point when there was taken a sample, that's statistic sampling. And then this is a very boring code because it does the same thing all the time, but if you have a more complicated flow through your code, you will see different colors, and then you can localize the areas of interest in your timeline. And I will come back to that when I'm talking about OpenMP. I use the performance tools also in a different course. I'm also teaching a Matlab course, and what we tell the students in Matlab is you should pre-allocate your arrays because that speeds up execution. But then the students ask why, and I did a little experiment. I hooked up the Matlab session to the collector, made a profile, and then I could show the students that if you don't pre-allocate, in this specific example, 98% of the Matlab execution time is spent in memory copy and memory set. So this is very nice to take a look behind the scenes. So another topic of the course is OpenMP programming. And here again, the compiler commentary is very useful because you can see what the compiler does, how it outlines the different parts of your code into functions and how it interprets the OpenMP you put into your code. And now there's another thing, the analyzer timelines. You get a timeline for each thread. And you can see if you have threads waiting on each other, if you have barriers and where you lose your time. And in the second part of my talk there, I have some example where you can see how this looks like. There's another nice tool that comes with Sun Studio, that's the thread analyzer. And one issue in doing OpenMP and POSIX threads programming is you are very prone to making errors that lead to data races. And the thread analyzer can help you to detect those data races. And this is, in my eyes, a very nice tool to make complicated issues visible to the students. And the nice thing is the thread analyzer is based on the analyzer, and the other tools the students already know, so there's no learning curve. It's just another plug-in to the analyzer. So there's no new tool to learn when we go from sequential programming to OpenMP programming. The tools are the same. Here's an example of the thread analyzer. Here I have a program with a lot of data races, and there are two windows. It shows you one thread has accessed this variable and another one at the same time. And you get, here it's the same code line, but it can also be from different parts of the code. One issue in OpenMP is scoping of data, and it's very important that you scope your data the right way. And the wrong scoping leads typically to data races or performance issues. And typically what we do in the course, that's what programs the students write themselves. But if you're working with large legacy codes where you have to think about the scoping of hundreds or thousands of variables, that can be a nightmare. And Dieter from Aachen, I don't think Dieter, I can see Dieter, no, he's not here any longer. And he has put in a proposal to the compiler people at Sun to ask them if this would be possible to let the compiler decide on the scoping. Because the compiler does an analysis of your code anyway, so maybe it can help you to do scoping. And as a result, there's an extension to OpenMP. It's not in the standard, but it's a Sun extension to OpenMP. That's automatic scoping of variables, and it's really, really useful. And even if it fails, if it can't scope all your variables, it will give you hints why it cannot do it, and then you can, as a programmer, can go in and help the compiler to resolve those issues. And I'll come back to that later. So to sum up this education part, we have used Sun Studio now for the last 4 years, and the students like it really a lot, and the questions are always got, is it available for Linux? And it was only available on SPARC Solaris, but now it's available and you can get it for free. There's a comparison I did for some time ago for the students, namely to where I compared GCC, Intel, and Sun Studio, the compilers available for the students for free, and also the Max Chrono library and the Sun Performance library. I did a typical example, matrix times vector. I think Ruud has a pattern on that one. And what I have here is, it's very hard to see, but there are two versions. There's a rogue version and a column version, and the green one is the good version, and the red one is the bad version. A good compiler can turn the bad version into the good version, and that thus the Intel compiler can do this and the Sun compiler can do it. GCC is not able to do that. Then I compared also the performance library, Sun performance library versus the Intel MKL. And the funny part was in this slide is that if I use the MKL together with the Intel compiler, it suddenly forgets that it can turn the bad version into the good version. What is more interesting is to see how the Sun compiler compares to GCC and Intel for large problems. If we go to larger problems, 10 megabyte data size and above, then the Sun performance library, that's the blue curve, outperforms the mass kernel library from Intel. And even for the compiler, the performance difference is not that big. It's less than 5%. And this is an early version of Sun Studio 12. It's not even the latest one. Ease of use. I think for me, when I looked at this example, it was much easier to use Sun Studio because it was one link line when I wanted to include the Sun performance library. And for the MKL, I had really to tweak my makefile and to other things. So it was much easier to use Sun Studio. Here's a success story in what we did in our HPC environment. This is what we do typically. We do HPC support for researchers. I had one chemistry colleague. He came with this code that's carbon molecules on the surface, like this polymer crush here. It's a 7,000 lines fortran code, has been used for at least 15 years. Lots of go-tos, common blocks, and everything in one source file. We did an analysis of the call graph, and we looked where we spent the time, and there was one subroutine where we spent 80% of the time, and this calls two other subroutines. So what we did now, the loop in this subroutine, we tried to make it parallel, and I said, okay, give it a try autoscoping. And that I put a default auto in it, and the compiler generated a parallel version. It compiled without warning, and it was a parallel version. And actually this took us really by surprise, because I would have expected that it gives me some hints that there are some variables it cannot scope, but it didn't. Okay, so we gave it a try, and of course we did some test runs. It didn't scale. Okay, we can take a look at this later. Different number of threads, different results. So that's a typical indication of a data race. And I guess some other people would have given up, but we used the thread analyzer to find out where the difference came from. And we found two variables inside the code subroutine that needed different scoping. So we added the scoping to the OMP pragma, and the data race was gone. Very nice. So now we have the scaling problem, and here's what I said before. You can use the analyzer, and what I did here was to mark everything that is okay, green, and the OpenMP overhead in red. What I can see here, there's one thread doing all the work, the other thread is waiting, then the third thread is waiting even more, and the last thread is literally doing nothing. And said, okay, bad compiler, but that was the wrong conclusion, because we have to blame our model. This comes from the physics of the model, and if we take this picture again, our simulation box is subdivided into cells like this, and then we have those cells layered on top of each other, and if you look how we distributed the work to the threads, and you can see thread number 1 has to do less work than thread number 2. That also corresponds to the analyzer plot. Thread number 3 has less work to do, and there's almost no work to do for thread number 4. So this was easy to solve. We changed the schedule. Instead of distributing the work in slices, we distributed it on a cell basis, 3 cells at a time, by changing the schedule in the OpenMP pragma, and then we got perfect distribution of the work. What you see in red here is not you cannot get rid of that one. And then I looked at the speed up and the scaling, and this scales nicely, even according to Amdahl's law, with a 90% parallel part of the code, and that's actually higher than what I would have expected from the 80% I saw in the first profiles. So that's really nice. Another example where we had a data race in a program, or not a data race in a program, but when this user approached me, he said, we have the same code that runs on 2 times the same CPU, but on 2 different machines, the E6900 and the E25K. The same CPU, UltraSPARC 4 Plus, 1.8 gigahertz. And I would have expected a difference in runtime. Those of you who are familiar with those machines know that there might be a longer runtime due to the layout of the E25K, but the difference was big. Thanks. And it turned out that there was a data race, so it was not the same run on both machines. Some criticism, no roses without thorns. Some improvement I would like to see in Sun Studio, better installation process, and if you make a tar bundle, then please include the performance library, because it's a nuisance for people who cannot use the standard installer that they don't get the performance library. Product updates, they should be installed after the installation automatically, so you don't have to go out and fish for updates. And it would be nice to get a bundle instead of going and pick up for each component of Sun Studio to a patch. And actually, your web page suggests that there are no patches for Sun Studio 12, but there are patches, because I know I filed some bug reports and the bugs got fixed, so there must be patches here. Make your compiler flags consistent over platforms and the different compilers. This helps if you have multi-language packages, like we use CoinOR, because this can be a nightmare if you use configure and configure cannot find out what the compiler options are. To conclude, it's a world-class product. I like it very much. My students like it. It's available on the platforms we have. It's easy to learn and easy to use, and all I can say is keep up the good work. And if you got interested in it, here's are the addresses where you can download it, and also where you can get support. And as we have heard, there's always, as with most Sun products, there's a strong community, and there are forums, and ask questions in the forum. The Sun compiler engineers are reading those forums, and they're also answering questions. And then you can file bugs or request for enhancements. I think that was everything. Thank you.